Welcome to today's lecture. So we're going to continue sets. What we learned so far? We learned that a set is a collection of objects. We use set notation, curly braces or curly brackets to denote a set. Sometimes it's easy to list the members of a set, some other times it's not easy. So sometimes we use roster notation, some other times we use set definition. Very well. So we know that when we have a set, order is not important. The order is not important. What's the meaning of that? It means that set including A, comma B is the same as set including B, comma A. There is no difference between them. Well, what if we have ordered pairs? Recall that. An ordered pair is denoted this way. We use parentheses A, comma B. So as you can see, there are differences between a set including two members and an ordered pair. Here we use parentheses. A comes first, and the second element is B. So your x coordinate is A, and your second coordinate or y coordinate is B. And remember that in general, ordered pair A, B is different from B, comma A. A, comma B in general is different from B, comma A. For example, if you have ordered pair 1 and 3, it means that your x coordinate is 1, your y coordinate is 3. Well, 1 and 3. 1, 1, 2, 3. This is 1, comma 3. But if you change the order, if 3 comes first and then 1, you get 3 and 1. You get two different points. So when you have ordered pairs, you should be careful which one comes first, which one comes second. Example for you. So I forgot to write down the objectives. There's not much difference from last time. We're going to talk about sets, relations, and then functions. Example, which one is true, which one is false? The first one says 1 and 2 is the same as 2 and 1. The second one says 3 and 5 over 10 is the same as square root of 9 and a half. And see, what do we have? What's the first element of 1 and 1? Okay, perfect. Let's see. 1 and 2 is of course different from 2 and 1. So this is false. We just mentioned that these are ordered pairs. You get 2 different points. They're different from each other. What about these 2? So when you look at the second ordered pair, if you simplify that, you get the square root of 9, which is 3. And here you have a half. If you simplify the first ordered pair, you get 3 and a half. So both of these are equal to each other and they are 3 and a half. So this is true. For part C, what is the first element? Even though the first element and the second element are the same, they have to say that, hey, they have to specify that this is our first element. Pretty easy. I saw this in algebra, pre-algebra, and there's a lot of confusion about ordered pairs. So remember last time we said that when we have a set like A or B, we can take a subset of set A and define a new set. The subset of A is a new subset, a new set. Okay, if you have the possibility they are equal to each other, remember that you use the notation subset or equal. If you are sure that they are not equal to each other, you use the symbol proper subset. So this is for proper subset. Never equal. But if you don't know, you're not sure about it, you use the general symbol, the general notation for being a subset. Now I expect you to ask, what other operations we can use to create a new set? This is our goal. Our goal is to create a new set by using one set, two sets, more sets. One of the methods that we're going to use is using Cartesian product between a set and itself or two sets. Definition. Cartesian product. So, as I mentioned, we have to have a set, at least one set. Suppose in this case, we are taking two sets. Let A and B be two sets. The Cartesian product is A cross B, first set, second set. Order is important for us. Is equal to the set of, the collection of. So note that here you're working with two sets. You have some elements from the first set, you have some elements from the second set. The set of, so the set of all ordered pairs. The set of ordered pairs, points in XY plane, for example, ordered pairs such that, with the condition that, such that A belongs to the first set, B belongs to the second set. A is in A and B is in B. Your first coordinate belongs to the first set. The second coordinate belongs to the second set. So since you have first coordinate, second coordinate, order is important for us. Well, let us go over some examples. This example here says, well, suppose you have two sets, let A be a set including 1, 2, 3, and B be a set including two elements like U and V. Very well. So question says, first of all, find the Cartesian product between A and B. A comes first, B comes second. B, find the Cartesian product between B and A. C, it says find the Cartesian product between B and B. And D says how many elements are in Cartesian product between A and A? What's the cardinality of this set? What's the cardinality of A Cartesian product with B, and B with A, and B with B? Okay, and it finally says, let R denote the set of all real numbers. What's the meaning of R Cartesian product with R? What is R cross R? Very well. So in this case, we know the definition. We know that A Cartesian product with B is the set of all ordered pairs A comma B such that A is in the first set and B is in the second set. This is the definition we just learned. So A Cartesian product with B, it's the set of all points ordered pairs such that the first coordinates are belong to the first set, second coordinates are belong to the second set. So you have A, U, 1, comma, U, 1, comma, B. The first coordinate is coming from A, the second coordinates are coming from B. Then the first coordinate is coming from A, 2, comma, U, 2, comma, B. The first coordinate is coming from A, you're left with 3. The second coordinate is in B. Well, how many elements do we have? We have 1, 2, 3, 4, 5, and 6 elements. The cardinality of set A is 3. The cardinality of set B is 2, and they don't have any common elements, and the cardinality is 2 times 3, 3 times 2, which is 6. What about the B Cartesian product with A? It means that in this case, all first coordinates are coming from the second set. So you have U, U and 1, U and 2, U and 3. First coordinate is coming from B, V and 1, V and 2, V and 3. Okay, perfect. How many elements? 1, 2, 3, 4, 5, 6. 2 times 3 gives you 6 elements. 6 ordered pairs that are all different from each other. Okay, what about the Cartesian product between B and B? It means that we're just combining the elements of B with each other. U, comma, U, U, comma, V, V, comma, U, V, comma, V. Okay, how many elements? How many numbers? 4 of them. So what do you think about the Cartesian product between A and A, and how many elements are there? We have the combination of 1 and 1, 1 and 2, 1 and 3, 2 and 1, 2 and 2, 2 and 3, 3 and 1, 3 and 2, 3 and 3, which is 9. So here we get the cardinality equals to 9. And finally, the Cartesian product between R and R. Remember that how we defined R. R is just the real axis. So if we only have R as the real axis, this is how we visualize this, how we represent this, the real line. You can say that, hey, this is my x-axis. Now it says you have Cartesian product between R and R. It means that we are adding a new axis, another R. This R, let us call it y-axis. The Cartesian product between R and R gives you all points belong to the plane. So all points in the plane or xy axis, xy plane, is R Cartesian product with R. So we're done with sets. We're going to talk about relations and then functions. So first of all, let me ask you this question. What is the difference between these two? The first one and the second one. Both of them are in plane. I have this guy here. I have this guy here. So what's the difference between these two? What do you think?
Their coordinates are different.
So what do we call this one? What do we call this one? What's the name for this? What's the name for this? Okay, equations, parabola. Okay, this is a parabola, of course. Okay, this is the name for it. The main difference between these two is that this guy doesn't pass vertical line test. This guy passes vertical line test. What's the meaning of that? Do you remember vertical line test? Line test. So we say that a graph represents a function if it passes vertical line test.
So the first one does not represent a function?
Very good. It's not a function, but this is representing a function. Excellent. A graph represents a function if it passes vertical line test, VLT. If you have any random vertical line, it has more than one intersection with the graph of with this graph, and it's not going to be a function. Not a function. Okay, it's not a function. What is it? This guy passes vertical line test. Any random vertical line has at most one intersection with the graph of the function, so this is a function. It means that for each x value, we can find only one y value that they are in relation with each other. So this is not a function. What is it?
A relation?
Very good. It's not a function. We call this a relation. What is a relation? Relation is a bunch of points in xy plane. It is a relation. It is a set of points in xy plane. But this is just a function because it passes vertical line test. We're going to officially define these two in mathematical point of view, in logical point of view. How do we identify this? It is a relation with some more conditions. So if you have a bunch of points following a pattern, not following the pattern, it doesn't matter. It is called a relation. Okay, perfect. So I'm going to write these side by side. Definition of a relation, and then definition of a function. So remember that we always start with sets. Let A and B be two sets. A relation is a subset of the Cartesian product between A and B. So we take A and B, we take any random subsets of points. Remember that Cartesian product between A and B represents points. And then we take a random subset, any subset, and we call it a relation. So let R be a relation as a subset of Cartesian product between A and B. If you have some points in this relation, remember that if you consider the Cartesian product between A and B, it might be represented this way. A lot of points in A, Cartesian product with B. Suppose this is your Cartesian product between A and B. What do? We take a subset of A and B, and we call it R. If a point x comma y belongs to R, we say that x is in relation with y. You write it this way, or you write it this way, x, r, y. Okay, so as we talked about, for example, if you think about a circle, for example, a circle, like a unit circle, x squared plus y squared equals to 1, a unit circle is a relation, not a function. Unit circle, you have some points in xy plane, and it doesn't pass vertical line test. But what is it? It is a function. It is not a function, it's a relation. So there are some points, and you just connect them all together, and you get your relation. Very good. So let us now define a function and see the main differences between a relation and a function. And I give you another example about relations so you can distinguish between them. So when you're talking about a function, visualizing that is easy. Vertical line test doesn't pass vertical line test. Relation passes vertical line test. It's a function. Again, we start by having two sets. Let A and B be two sets. Okay, the notation that I used here is, okay, a relation with domain A and co-domain B. So you take your first set, and since you always start from the domain, let us call A the domain. And you end up or stop at the second set, we call it codomain. A relation like F with domain A and codomain B, which represents this way, F A to B, is called a function if it satisfies these two conditions. First of all, for every element in A, we can find another element in B, such that they are connected together, they are in relation with each other using F. And second condition, this condition is about passing vertical line test. If x comma y is a point in F, if x is related to y through F, and also x comma z is another element in F, then you can conclude that y and z are the same. If these two conditions are met, we say that F is a function between A to B. We usually use arrows to represent this relation from A to B. This is your F. Taking elements from A, mapping them to set B. So remember that this condition, the second condition, is equivalent to vertical line test. So how do we visualize the second condition? The second condition, think about it this way. Here you have, for example, this curve representing a relation. It says if you have, for example, the first point, x and y, on the graph of the function, and you have another point, x and z, on the graph of the function, so x values are the same, y values must be the same, of course. So y and z must be the same value, otherwise it doesn't pass vertical line test. Y is equal to z. Think about this way. This is a function. Consider this curve here, this relation here. And you're taking 2 points. You already know that by vertical line test, it's not a function, but what? So take 2 points, x and y. X is the same, x and z. Y and z are the same? No. Y is here, z is here. It doesn't pass vertical line test, so it's not a function. To be a function, if you have 2 points with the same x value in that relation, the second coordinates, the second values must be the same. Otherwise, you don't have a function. Two examples for you. Well, this example says let A be a set including 1 and 2, and B be a set including 1 to 3. Define a relation like R between A and B. Define a relation between A and B. R as a subset of Cartesian product between A and B such that this relation satisfies this. You say a point is in the relation, belongs to that subset if and only if, or meaning that x minus y divided by 2 is an integer. Belongs to Z. How do we define this relation? Okay, first of all, what is Cartesian product between A and B? Cartesian product between A and B is the set of points from A to B, all the combinations. 1 and 1, 1 and 2, 1 and 3, 2 and 1, 2 and 2, and finally 2 and 3. Okay, this is the Cartesian product between A and B. You're looking for a subset, or as a relation is a subset. You're looking for a subset of A Cartesian product by B such that if I take the first coordinate minus the second coordinate divided by 2, it's an integer. Remember, Z is the set of signed numbers. -3, -2, -1, 0, 1, 2, 3, and the rest of them. Okay, so since I'm working with a subset of Cartesian product between A and B, my choices are limited or restricted to these pairs. Let us start by the first one. 1 and 1. Take a look at this. The first coordinate is 1, the second coordinate is 1. 1 minus 1 divided by 2 is 0 over 2, or 0, which is an integer. So 1 and 1 is the first member in R. What about the second one? 1 and 2. Okay. 1 comma 2. 1 minus 2 divided by 2 is -1/2, which is not an integer. So is not in R. What about the second one? Sorry, what about the third one? 1 and 3. Okay, 1 and 3. 1 minus 3 divided by 2, -2 over 2, -1, which is easy. Okay, perfect. I found another point in this relation. I'm going to continue this process. 2 and 1 is not. 2 and 2 is. 2 and 3 is not. A member of R. So you can say that, hey, my relation that satisfies this condition is going to be the set of these points, 1 and 1, comma, 1 and 3, comma, 2 and 2. This is our relation. Satisfying x minus y divided by 2 belongs to Z. So we don't have much to worry about relations. It's just a collection of points or ordered pairs. But when it comes to functions, you always have to be careful. Make sure all conditions are met. For example, so this is functions, that last one. For example, question says, let A be the set including 2, 4, and 6, and B be the set including 1, 3, and 5. 1, 3, and 5. Where which relation is a function? So the first one here says you have this relation, a bunch of points, 2, 5, 4, 1, 4, 3, and 6, 5. How many points are in this relation? 4 points. Another relation is defined as for all X and Y belongs to the Cartesian product between A and B, we say that X is in relation with Y in S means that Y is X plus 1. And finally, C, relation T is defined this way. From set A to 4 and 6, we map it to the second set B, which has 1, 3, 5, and we define this relation this way: 2 to 5, 4 to 1, and 6 to 1. Which one is a function? Okay, remember when you're talking about a function, all elements in the first set must be assigned to an element in the second set, from the domain to codomain. Okay, let us take a look at our first elements. First elements, 2, 2, 4, 4. Okay, another 4, you have it here, and 6, and 6. They go to 5, 5, 1, and 1, 3, and 3, 5, and 5. So all elements in the first set in A are assigned to an element in B. The first condition is met. We don't have any problem with the first condition. First condition is met. Now we have to move on to the second condition. Vertical line test. We know that if, second condition says, if X and Y are in this relation, X and Z is also in this relation, then we should be able to conclude that Y and Z are the same. Is this condition met? Okay, take a look at this. You have 4 and 1, 4 and 3. 4 and 1 belongs to R. 4 and 3 belongs to R, but 1 is not the same as 3. They are different from each other. So second condition is not met. So this is not a function. Not a function. You could just graph this and actually see it doesn't pass vertical line test. You get 1, 2, 3, 4 points in XY plane, and it doesn't pass vertical line test. It is not a function. What about part B? Let us check these conditions. The first condition, let us check the first condition. Okay, here we go. First of all, what are the elements in this relation? Y is equal to X plus 1. So if X is equal to 2, let's see. Y is X plus 1. So take a look at this. Let us write down the elements in this relation. Your S is equal to. If X is equal to 2, your Y is equal to 3. If X is equal to 4, your Y is 5. Well, if X is equal to 6, your Y value is 7. Take a look at this. 2, 2, 4, 4, 6, and 6. We don't have any problem with the first elements. We took them all from the first set. Our problem is with second elements. I have 3, 3 is here. I have 5, 5 is here. 7, I don't have any 7 in B. So, first condition is not met. We have 6 in the set, which is not assigned to any element in the first condition is not met, so it's not a function. Not a function. How about this one? Relation between A and B defined by T. So what is T? T is this set. 2 and 5, 2, comma 5, 4, comma 1, and 6, comma 1. All elements in the first set, 2, 4, 6, 2, 4, 6 are assigned to some elements in the codomain. 5, yes, I have 5 in the codomain. I don't have any problem here. But 1, yes, I have 1 here. Of course, another one, yes. Okay, the first condition for being a function is met. How about the second condition? Does it pass vertical line test? Take a look at this. If you graph this, you have 2 and 5. 1, 2, 6, 2 and 5. This is 2 and 5. 4 and 1. 4 and 1. 6 and 1. 1, 2, 3, 4, 5, 6, 6 and 1. So does it pass vertical like this? Of course. You have 3 points. If you have any random vertical line, it has only one intersection with the graph of this relation. So this relation is a function. Is a function.